The Cohen-Specker theorem denies the pre-existing value of an observable. Is the outcome of a measurement the result of the observer's personal gambling? That's the problem. So here, we shall show that quantum mechanics answer the question so that only the first case occurs. That is, those two observers obtain the same perfectly correlated outcomes of the measurement. We suppose those observers are space-like separated. They place very remotely. This suggests that the common outcome of the two measurements has pre-existed before the measurement. In contrast to the common interpretation of the Cohen-Specker theorem. We also show that the state-dependent approach enables quantum mechanics to answer the question affirmatively. I'd like to start with our assumption, postulates for quantum mechanics. We assume very conservative set of the postulates. The first postulate determines what is the mathematical representatives of quantum systems, observables, and states. Quantum systems are represented by Hilbert space, and observables are represented by self-adjoint operators, and states are represented by unit vectors. And the second postulate is the Born formula for commuting observables. We consider only two commuting observables here. For any commuting observables A and B, a probability of the value of A to be X and the value of B to be Y is given by this formula, the inner product of the psi and PAX PBY psi. Here, PA denotes the spectral projection of observable A. So the PAX means there are spectral projection of A corresponding to the value X or eigenvalue X. The third postulate is the usual Schrödinger time evolution. For any commuting observables A, B, the probability of A of t has a value X and B of t has a value Y in state psi is equal to the inner product of the UT psi and PAX PBY UT psi, where UT is the unitary evolution operator, is postulated to be exponential of minus ITH over H bar for the Hamiltonian age of the system. Then we consider the observer independence of the outcome of measurement. Denoted by S, the system to be measured, described by Hilbert space H, and E to be the environment. This is external system, external to the S. The environment is described by Hilbert space K, and A to be an observable of S to be measured by two observers, and then M1 and M2 are two commuting observables in environment E, representing the meters of the two remote observers, observer 1 and observer 2. Then the time evolution of the total system of the system S and environment E with the total Hamiltonian H on Hilbert space H tensor K determines the Heisenberg operators A of 0, Mj of T, where J is 1 or 2, represent the observers, and with time 0 time T positive number. And we assume that the T is a measurement interaction start at time 0 and end up at the time T for both observers. For simplicity, we can assume time of the measurement T can be different to observers 1 and 2, but for simplicity, we assume they are same. Where A of 0 means the H tensor identity operator, and MJT is UT dollar times identity tensor MJ times UT. MJ is the operator on the Hilbert space K, and UT is exponential minus ITH over H bar. Then let psi and xi be the initial state of the system S and environment T at the time time 0. And then POVMs of the two observers are defined by pi jy is equal to partial inner product of the C. C is in the vector in K. C times P MJT y in C. So this defines the partial inner product over the Hilbert space K, and PMJTY is a projection on the Hilbert space H tensor K. So this formula defines a positive operator on the Hilbert space H, just like partial trace. And this pi jy is a POVM, a positive operator by the measure, normalized to be unit operator for the totality. Then observer J obtains the outcome X in the system state psi with the probability MJT is equal to X in the initial state psi tensor Xi is the inner product of psi, pi jx and psi. This is our usual formula to determine probability from the POVM of the measurement. So equation 9 determines the probability of the outcomes of the both observers 1 and observer 2. Then our assumption is that only this assumption we assume that the two observers reproduces the probability distribution of A correctly. Namely, we require this output probability distribution is equal to the postulated probability distribution of the observable A in the state system state psi. Xc is a fixed state of the apparatus or environment. So we require this equation 8 to hold for any state of the system psi. So this is equivalent to the P of M of the measurement for both observers equal to the spectral projection PAX. Then, since M1 and M2 commute their joint probability distribution, and the system state psi is given by the following formula. So joint probability distribution for the outcome of observer 1 to be X and the outcome of the observer 2 to be Y is equal to this inner product for psi tensor axis state and P M1Tx times P M2Ty applied to this state psi C. So this is the usual probability formula for joint probability distribution for commuting operators M1 and M2. Thus, the quantum mechanics can answer whether the above joint probability distribution is perfectly correlated or uncorrelated, because anyway, those probability, joint probability is defined inside the quantum mechanics because M1 and M2 are commuting. Then we can obtain the following theorem. The outcomes of the measurement of A by the two observers are identical. That is, this joint probability distribution for the value X and value Y is equal to 0 if X and Y are not equal. So this joint probability distribution is concentrated on the diagonal for X and Y are identical. This relation can be proved based on the theory of the quantum perfect correlation developed in my paper published in 2006 in Annals of Physics. Now we consider the conflict between this result and Cohen-Stecker theorem. Because if we don't have any, we don't assume any pre-existing value of measured observable, why can we obtain the same outcome in a remote observer? Not only just reproduce the probability, but also why they reproduce the same individual outcome. This theorem suggests that the measurement reproduces the pre-existing value. This means that joint probability of the A0, or the value of A just before the measurement, and MJT, the value of the meter just after the measurement, it should be perfectly correlated. So we can imagine this can be a whole, because this is a common cause of this perfect correlation of the two remote observers. However, this is a difficulty. There is a difficulty in this above formula, since A0 and MJT are not necessarily commuting. A and MJ are commuting observably in the same time, but we should compare the A at the time just before the measurement and M just after the measurement. So they are different time, so not necessarily commuting. However, we shall show that A0 and MJT are essentially commuting. And this equality actually makes sense to hold. So in order to formulate those joint probability, we introduce state-dependent commutativity. Von Neumann observed that any observables x and y are commuting on the subspace generated by the common eigenstate of x and y. So we define as follows. We say that x and y are commuting in a state psi if psi is element of this common of this subspace generated by the common eigenstate, because on this subspace, those two observables can be treated as the commuting observable. And then we introduced another definition about the joint probability distribution. Mu xy is called the joint probability distribution of x and y in state psi if they satisfy the following formula. This formula means that for any polynomial f of x and y, the quantum mechanical expectation value is equal to the classical expectation value computed by this joint probability. If this is the case, we call mu xy to be the joint probability distribution of x and y in state psi. Then we obtain the following theorem. The following conditions are equivalent. X and Y are commuting in state psi, and the second condition is actually those two spectral projections are commuting on this state, and joint probability exists, and psi is a superposition of a common eigenstate, and then this conjunction of the spectral projection sum up to identity on the state psi. All those conditions are equivalent, so they characterize the existence of the joint probability by the commutativity of the observer at the state. In this case, we obtain those probability values are equal. So the joint probability can be represented by those terms. So this is just the usual formula for the joint probability distribution for commuting observables. It's the same form. So we obtain the state-dependent Born formula. If x and y are commuting in state psi, we define the joint probability as the usual formula for globally commuting observables. Then we introduce the notion of the quantum perfect correlations. We define, we say that x and y are perfectly correlated in state psi if x and y are commuting in state psi and joint probability distribution exists, and this shows the perfect correlation in classical sense. Then we have the following characterization theorem. X and y are perfectly correlated in state psi. The following conditions are equivalent. So first condition is x and y are perfectly correlated. The second condition is psi is a superposition of common eigenstate of x and y with common eigenvalues. So psi is a superposition of the ket x is x has a value x, and also y has the same value x. So this means that this ket is a common eigenvalue of the x and y with a common eigenvalue x. And also the third condition is this some of those conjunction of the spectral projections with the same eigenvalues applied to psi is just like identity on psi. Then we have the following theorems. It is important. This relation of the perfect correlation in a given state is equivalent relation. In particular, it is transitive. So if X and Y are perfectly correlated and Y and Z are perfectly correlated, then X and Z are also perfectly correlated. This is very nice property because the commutativity is not transitive, but this identicality can be the transitive. Then we obtain of this framework, we can formulate the following theorem to be true. If a measurement of A with a meter MT has the correct P of M, that is, the P of M pi is equal to the spectral projection of A, then A0 and MT, so the measure observable to be measured at just before the measurement and meta observed at the time just after the measurement is perfectly correlated in the system initial state for any state psi of the measured system. That is, there are joint probability of A0 and MT exists, and the joint probability shows the perfect correlation for any input state psi. So this mathematically shows that measurement outcome is equal to the pre-existing value of A just before the measurement. And this value reproducibility and the observer independence, the first theorem, is a very close logical relationship. So we can prove the observer independence from the value reproducibility using the transitivity of this perfect correlation. So we can prove the theorem 1 using theorem 5. So from theorem 5, we have the A0 and MTJ are perfectly correlated. Then by transitivity, M1T and A0 are perfectly correlated, and A0 and M2T is also perfectly correlated. So by transitivity, M1T and M2T are perfectly correlated. So this means that joint probability of M1T and M2T exists and show the perfect correlation in the classical sense. This is just our first theorem for observer independence because this shows that if the remote observers 1 and 2 measure the same observer A in the same time, then they obtain not only the same probability distribution, but also they obtain the same outcome each instance. That's all my presentation. Thank you very much for listening.
Thank you for this talk. We have time for questions.
Could you explain how these two observers make the measurements at the same time on some physical system? Because of course mathematically it's nice, but I don't see how you imagine the experiment which could be done.
Oh yes, there are many ways that, for example, we have the one probe and the object to the probe. So this can be in the first. There are two stages. First stage, and we have the one apparatus. So we interact with the sub-object and the apparatus. First apparatus. Then observer 1 interacts with this first apparatus, and at the same time, observer 2 interacts with this apparatus.
But you know, in quantum physics, we learn that the measurement is disturbing a system. So it's and also it's not it's not simultaneous measurement by two observers. Especially you are talking about also distant measurements. So probably I don't understand. Okay, sorry. I should perhaps read your paper to understand how you imagine this experiment.
Robert Griffith has his hand raised, so.
Yes. Can you hear me?
Yeah.
Yes.
Yes. The fact that measurements reveal prior values is well accepted in the community of experimental physicists. So what I think is needed is people pay attention to how measurements actually reveal prior properties. And I've been pointing out how to do this for many years. I'm just sort of surprised that this idea hasn't gotten around. And of course, if the measurement reveals prior properties, then you can have however many probes you want, but they're all revealing the same property. And then the answer is obvious, isn't it?
You cannot use the same time two probes on one system, what I'm saying.
But this is the assumption. If you can do that, then you always have the same outcome. But you cannot prove that it is impossible. And we have the many examples.
Yeah, there are observables which are which exist before measurement. You know, they are like a charge of electron and things like this. But there are also quantum observables which, according to fathers of quantum mechanics, did not exist before. These values don't exist before being measured. You know, and for example, projection of spin. There is no projection of spin in general. Only you obtain it when you pass the system by a filter, a particular filter. Okay, thank you.
Von Neumann's book, the von Neumann argued that the some cases in which there are one interaction gives the two result of measurement. And in that case, the two result of measurement always coincide. And this theorem proves very generally in this von Neumann's observation.